All right, let's dive right into the fascinating world of cybersecurity and break down a really clever hack known as a heap overflow. You're going to see how a tiny, tiny programming flaw can be blown wide open for a full system takeover. So, here's our game plan. We're going to follow this four-part story, taking us from, understanding the basic flaw all the way to a successful hack. We'll look at the vulnerability itself, the attacker's initial plan, a major roadblock they hit, and finally, the absolutely brilliant solution they came up with. Okay, first things first, let's get a feel for the playing field and the specific vulnerability we're dealing with, because this isn't your everyday, run-of-the-mill overflow that you might have heard of before. So what is a heap overflow exactly? Well, it happens when a program tries to stuff more data into a memory buffer on the heap than it was actually built to hold. Just imagine pouring way too much water into a cup. It's gotta spill somewhere, right? And where it spills, well, that's where the trouble really starts. Now, you've probably heard of a stack overflow, right? Well, this is different. Think of the stack like a neat pile of plates. Last one on is the first one off. It's super structured, very predictable. The heap? Oh, the heap is more like a junk drawer. Stuff gets thrown in and taken out all over the place. That messy nature makes heap overflows way trickier to pull off. But, oh boy, when they work, they are just as devastating. Okay, time to put on our detective hats. Let's go find the exact chink in the armor of our target program. Because, every great hack starts with some solid recon work. Our target is this little program called Secret. Seems pretty innocent, right? All it does is let users write little notes. But, and this is a huge but, it's been given special root permissions. That means it's running with God mode access on the system. And that's the golden ticket for an attacker. So how do you find that weak spot? Well, an attacker has a pretty clear playbook. First, they dig into the source code. Then, they fire it up in a debugger to watch it run in slow motion. They're basically mapping out the program's memory, trying to find one specific thing, the exact distance between the data they can control and the critical variable they want to hijack. And after all that digging, all that detective work, it comes down to this. One single number. 11 bytes. That is the magic number. You see it? That 112 bytes? That is the exact size of the buffer. It's the key that unlocks this whole thing. If an attacker inputs a string that is precisely 112 bytes long, byte number 113 is going to spill over and start overwriting whatever comes next in memory. And that is exactly what they want. All right, so we found the vulnerability. Now for the fun part, the actual plan. How do we turn this little memory overflow into the ultimate prize of gaining root access? Because, finding the flaw is just step one. The whole plan hinges on this one file, /etc/password. Now, if you're not a Linux geek, just know this. That file is basically the user account Bible for the entire system. If you can add a line to that file, you can literally create a new user out of thin air. Any user you want. And this is the prize. The line they want to add. It's perfectly crafted to create a new user called Hacker1. But look really close at those 2 zeros. That's the user ID and the group ID. On any Linux system, ID 0 means one thing. Root. The super user. The boss. But there's a problem. A big one. The attacker hits a wall, a snag that could just blow up the whole plan. Turns out, getting the program to write this exact string isn't quite so simple. Yeah, the program itself is the problem. It's actually trying to be helpful. Since we're telling it to write to the etc. password file, it automatically tacks that file name onto the end of our secret note, which, completely messes up the required format. The new line is now total garbage, and it looks like the whole exploit is dead in the water. But this is where things get really, really clever. A simple but absolutely brilliant trick that turns this roadblock into the finish line. The attacker isn't going to fight the program, they're going to use its own helpful behavior against it. It's a beautiful bit of misdirection. First, the attacker creates something called a soft link. You can just think of it like a shortcut on your desktop. They name this shortcut /temp/etc/password, but it doesn't actually point to a password file. It points to something completely different, /bin/bash, the system's command shell. Then they build their new malicious string around this decoy path. So check out the final payload string now. See that last part? The part that's supposed to be the user's default shell? It's our decoy path /temp/etc/password. The idea is to use the heap overflow to trick the program into thinking this decoy path is the file name it needs to write to.
Okay, so here's how it all comes together. The attacker crafts the string using that user info field to pad it out to exactly 112 bytes. That triggers the overflow, and bam, the program's real file name variable gets overwritten with their decoy path. Now the program writes the entire malicious string to the real /etc password file, and when the system reads that new user entry, it gets to the end, sees the decoy path, follows that shortcut, and makes /bin bash the new user's shell. A perfect root user is born.
And that's it. Game over. The attacker can now just log in as the brand new HackerOne user, and they are root. They have complete and total control of the entire system, all thanks to one tiny overflow and a ridiculously clever trick.
So what's the big takeaway here? This whole exploit is just a brilliant reminder of a core principle in cybersecurity. It's not always about the big, obvious, glaring flaws. Sometimes it's the small, predictable, seemingly helpful program behaviors that can be twisted and turned to create the biggest security holes. It really makes you wonder, doesn't it? What other hidden assumptions are just sitting there, waiting to be broken?